what are GD&T symbols?
Geometric dimensioning and tolerances.
Yeah.
Tolerance symbol.
Yeah, geometric dimension tolerancing. But what do the symbols mean? What do I mean when I say GD&T symbols?
What do you mean?
Yeah, what do I mean? What are GD&T symbols? What symbols of what?
Symbols to identify different parts of the drawing or planes, or
They tell you how precise a part is.
No. The symbol doesn't have anything to do with precision. What does a symbol represent?
tolerances.
No.
Reggie, you should know.
What are some of the symbols? Let's start there.
ANSI codes.
No.
Center lines.
No.
Concentricity.
Concentricity.
Oh,
Cylindricity.
that's what you want to know?
Cylindricity.
Yeah, angularity,
Position.
Angularity.
parallelism,
Position.
Orientation.
Those are the GD&T symbols. So what do those
There's
represent?
5, right?
No, there's a lot of them.
Oh,
Yeah.
There's
Looks like
There's 5 main ones that branch out to
No.
others.
So what do those represent?
Different pieces of the part.
No. Just in
Different
general, what does it
tolerances.
represent?
Tolerances?
no, the condition
No.
of location.
Something about the part, right? Something about part of the part.
Condition of the part.
The condition, maybe? So the shape condition of it, how it's shaped, right?
That would be tolerance.
Cylindricity is the shape. Or this has nothing. There's nothing. Tolerance
Tolerance had to do with
means
the-
there's a size associated with it. Right now, there's no size associated with the symbol. What are basic dimensions? So we'll get back to those. What are basic dimensions?
Line.
have no
a
tolerance.
theoretical exact size.
So you got it perfect. It's a dimension with no tolerance at all. So haven't we already talked that all dimensions have a tolerance? And everything needs a tolerance? So how can we have one that doesn't have any tolerance?
Because they don't require it.
But everything needs a tolerance.
Because they locate a tolerance zone.
Because they locate a tolerance zone. So like position, this is going to control the size of the tolerance zone. So the dimensions that locate the center of this, we don't want any tolerances, or else we're going to get double tolerance. How do we represent a basic dimension? Yeah, we put a box around it. And that tells us that that dimension has no tolerance. What's a feature control frame?
Symbols and tolerances.
Well,
A box with symbols and tolerances.
Yeah, it's the box that contains symbols, the tolerances, the datum references, and a condition, right?
MMC and
So that's kind of like the call-out that we have. So feature control frame could be
position, diameter,
Tolerance.
your MMC,
And then
your,
datum.
and your MMC part.
so it could be something like that, right?
Yeah.
And then what's a datum?
It's, I found that too.
Yeah, the reference from where we're going to measure
Actual component.
for the tolerances. So that's kind of our reference point of where we're going to measure from. So here's the standard. NC ASME Y14.5 is dimensions.
Is that
So
that's
far-
the newest one?
This is 2009. So far, everything we talked about the last 2 weeks is right here. This is the last 2 weeks of regular dimensioning, tolerancing, limits and fits. That's all right here. The rest of this is GD&T. So 2 weeks we spent talking about how to dimension, all the parts about where we dimension, where we put dimensions, how we do regular tolerances. That's all this. That's, I don't know, 26 pages. And then the next 100 and 75 pages is GD&T. So I also have 3 other books that you can look at that are just on GD&T. So instead of just the chapter in our book, if you want to get more on it, there's these plus the links I put on Moodle. And we are not going to cover everything about GD&T in the class today, this week and next week, because it's just too much. Okay, 2 weeks?
Yeah, spring break's on the 9th, I think.
Yeah, in 2 weeks.
We have this class.
Yeah, we're going to be here on Tuesday for class next week.
Oh, that's not.
So, on the standard Y 14.41,
Are you gonna be here next week?
no,
Okay.
Y 14.41, 2003 standard. This was the one that introduced that made it acceptable to dimension 3D models. It's still not widely used. There's still debate about how to do things, and some of the software packages don't really support everything in here. So even though it says we can do it, Inventor and SolidWorks don't do everything that this allows for. So usually we still, if we send the model, we'll just send them regular 2D drawings. We won't send them an annotated model like this. So just to show you kind of where it's going. So when we make a drawing, the drawing gives us what? Size and shape, right? Size and shape, right? We already talked about that. So the tolerances we talked about last week affect what? The size. But it had nothing to do with the shape of the part, right? So what GD&T does is it affects the shape, the geometry. So here we have this part. You can see it still has size tolerances for everything. We still have a size tolerance for the diameter of the hole, a size tolerance for the outside of the cylinder, a size tolerance for the thickness there. We still have the size tolerances. Now we also have some shape tolerances. So the position tolerance on where these holes are located. Here, that this feature needs to be perpendicular to that. But this backside needs to be flat. So now we're giving it a lot more control over specific parts and specific features within the part.
Now, on the, like say for example, on that piece, just giving it a flat symbol won't do. You have to actually give it a tolerance for it?
Yeah. Because if you just say flat, what's your tolerance? Nothing's perfect. Nothing's going to be perfectly flat. Even glass isn't perfectly flat. Mirrors aren't flat. Polished things aren't flat.
Water to vacuum is.
That's not a manufactured thing that you're going to be able to live with. Nothing is flat. Nothing's perfect, so you have to have a tolerance on everything. So remember we looked at surface finish. Last week we talked about it briefly at the end. Those numbers are micro inches. So you got the surface finish, but then you also have the flatness, because the surface finish is how flat it is, but it's still got waves in it and stuff. So we're telling it that's flat. Now that this feature, this outside cylinder, has to be perpendicular to that. Something like that, okay? So there's a lot of stuff in there. And so GD&T really lets you know the function of the parts and what's important, and helps to keep things aligned with how they really need to be. think I have this one later on, where we're gonna go through and look at some of this stuff. So, we're gonna talk that drawings are not made exactly to the drawings. And so GD&T allows us to have looser tolerances, but it make them more accurately. So what does that mean? How can I have a looser tolerance and make the part better?
Because of the exact spacing between the actual dimensions.
Well, not just space between the dimensions, but let's look back here. So let's look at this one. If I didn't have the GD&T and I wanted this back surface to be flat, what would I have to do? Or let's say how much can this back surface vary right now?
5,000.
This surface right here, so let's imagine this surface was perfect. Or even where you measure from. This one could go out 5 thousandths and in 5 thousandths. Out 5 thousandths and in 5 thousandths. So it could really be 10 thousandths of an inch, not flat, right? From the peak to the valley. And so if you wanted to control that, to keep it flat within that, you'd have to make this tolerance with an extra 0 on it, right? You'd have to make it 5 thousandths plus or minus to keep that flat. But now by adding the GD&T on it, we can say, here's our little, that's where it can be. It can be somewhere between there, as long as this line is bigger than that, and that line is bigger than that. So that we've got a zone, but that whole thing can only be that thick. So now that the flatness can move in and out a bunch, still be flat, but allowing it to move. See how that can kind of help a little bit? Gives us bigger tolerance here, while still keeping that tolerance that we want.
So even if they made it 0.7 thousandths of an inch?
What do you mean?
Like even as long as it's before the...
What do you mean 0.7?
Like between the two. So if they made it like 0.007, I mean 0.07, that would make a difference, right?
0.07.
Between the 10.
Between the max and the least.
The maximum limit.
Yeah, as long as where the surface lies is between those two numbers, and the overall difference between the minimum maximum of the surface is that, then it's good.
What is that 1,000 dimension?
What?
What is that 1,000?
This?
The valley and. Or the
Yeah, it's measuring
surface?
from any point to the width. So, like if they put this on a surface plate, so like the surface plate over here, we put that down here and put a dial indicator on it and drag it across it. The high would record what the high number was, record what the low number was. And the difference between those two would have to be less than 1,000ths apart.
Okay.
And then it'd pass. Questions? Alright. And we'll talk more about that later. But remember that we're trying to, it's a little bit more complicated, but it allows us to have a lot more variation. So kind of one of the best
Did you
examples.
finish the last part? I know you were going to go back to something, then I stopped you. We were,
No, that was it.
oh, okay.
So kind of position is a good example of this. So if we had it plus or minus 0.02, this is the shape of our tolerance zone. So that's a square, right?
Yeah.
How far can the center of that hole be out of position? What's the maximum distance it can be away out of position? Remember the tolerance for that hole was
0.04.
plus or minus 0.02 in the x and in the y. So how far away from that center point can the center of the circle really be?
0.04?
So 3.
So it's close.
So it's the center can actually be further than that, right? So if the part was made and the center was there, it's a good part, right?
Yeah, so good.
The part was made and the center was there, it's a good part, right?
Yeah.
If it was made there, it's a bad part.
Yeah.
And it's outside.
But this circle is closer than that one. So why is that a bad part?
Because it's outside
Because
the
it's
peripheral.
outside the zone.
But it's closer than that.
Still outside
That's
the zone.
closer to the center than that one is.
But it's the
But
shape.
it's outside the zone.
But it's the shape of the part.
But that's because of the shape is a square, right?
Mhm.
But functionally, would that be a good part?
No.
So it
Yes.
depends on
If
what
this one works,
Because
if the hole's over here and it works, would the hole being there work?
No.
Probably not.
Sure.
It depends.
Depends on what it's
Because
joining to.
if that, is that a shaft?
Doesn't matter.
How can it not matter?
If we have two holes and they're lining up with each other, we have our clearance in there, right?
Yeah,
And so that's set up so that way the hole can move around
right.
and the pin or whatever that goes in can always fit in, right? With a certain amount of clearance. So it doesn't matter if it's that way or sideways. It has the same amount of movement in all directions. It was still having a clearance.
So then wouldn't it be smarter to, instead of doing the square, do a circle,
Exactly. So instead of doing the square zone,
do a radius?
because this one would work. That one would work. So instead of making that a bad part, why not make it so that we include all that? We include that area out here, so it's that same distance around.
Well, sure, if you want to change the rules, then you can play the
That's what we're doing. GD&T
Right.
is making it so we can include that whole circular area.
Better than
It's not bending them, it's making better rules.
Adjusting.
And so we're actually getting like 67% more space. And so,
But what about in situations where you need that particular size or that particular type of
No.
shape?
give me an example.
Like for example, say that's a cap to a pipe or something, right? And it needs a square part so you can twist
This
on.
isn't a part that's square.
Well, I'm
This
just
is
saying.
the tolerance zone.
Well, say you need a certain amount of tolerance, so it has only a certain amount of things, so the pin can stick on and twist.
It's not,
That's not what this is.
you're not talking about the shape of a part.
You're missing
just
the
talking about
whole.
the zone.
The whole idea is that, remember last week we talked about tolerances, the clearance fits, where the shaft is always going to be smaller than the hole.
Mhm.
And that it could vary how much that space is, but there's always going to be a gap in there.
Okay.
This is controlling how to line up those two holes so that way when the holes change size, they're always going to the pin's going to go through. Doesn't matter orientation, because this is just the pin that goes in here is always going to move around.
Yeah.
And so talking about it locking doesn't have anything to do with this. That'd be a whole nother set of problems. Yeah.
If you were talking about drilling a hole in the end of a part that rotated, say, camshaft, is it possible that your target area instead of being a circle would be an oval because you want it to go more one direction versus the other?
But what is that lining up with?
With another hole?
Yeah, so it's usually you'd want it to be circular position zone where that center could be, because you have your perfect alignment, and then the slop around that. So that would make it even worse, because then you could say you can be more out this way, then you can be out that way. That really doesn't make a whole lot of sense. No.
Unless you're trying to stay away from having it go out those directions, is what I'm saying.
No.
But you're still talking about the center of that camshaft
Yeah.
needing to be lined up. So if you're allowed to be outside that center more, then it's going to wobble even worse.
Yeah, because
They go this way.
you're talking
You'd want to have the same.
GD&T, which affects the shape.
Because what you're talking about,
Can be
if you have that
hole.
If you have that shaft here, there's your center line, and so you want that to be evenly spaced up and down, or all the way around it, right? Because if you made it so you can go further here, then it's gonna be further away from the center and it's gonna wobble. So that's not really what we want. So the whole idea is we want it to be a round zone instead of a square, so we can get some extra space. So when we're putting the center of that zone, we don't want any tolerance on it, so we're going to make it a basic dimension, right? Because we're going to have a new tolerance zone. So if we have a tolerance on the dimension that positions the center, then it would kind of stack and actually double it. So we already talked about that being a square around it. So these two dimensions are positioning the center of that hole in the perfect location, and now the tolerance is being carried over here and telling us we have a diameter of 0.06 for that zone. Make sense? So here is a radius of 0.3. Now I have a diameter of 0.06.
Oh, yeah. It's half.
So now we've got 67% or so more space to work with, so that would be a good part. So rule number one, this is just called rule number one, is that if it's just a numerical tolerance, then that tolerance controls both the size and the shape of the feature. So if we have that dimension, diameter of 1/2 inch plus or minus 5 thousandths, does it have to be perfectly round? Does that mean that that's a circle? A perfect circle?
No.
So you said no.
Well, no, it's a circle, so I guess it would.
But does it have to be perfectly round?
It's perfectly round, it's just whether it's larger or small, or larger.
Yes.
Is that what it's saying?
Yes.
That it has to be a perfect circle with a
Yes.
diameter of 495 or a diameter of 505?
Yes.
My
Is that what it's saying?
Yes.
That's my guess.
No, it's not.
No?
I
What
meant
this
no.
is saying is that it can be an ellipse with this dimension
495.
And that one being 505.
It could be that and still pass. Or it could be as long as the smallest diameter
The fuck?
as long as any measurement across that
Meets those
That-
measurements.
Well, then what do you mean that that dimension controls both the size and the shape?
that's controlling the shape, right? It's meeting the size and the shape. So I can't say it needs to be perfectly round because it meets the size requirement. So that size requirement is even that shape.
That could be any shape, basically.
So as long as it meets the number dimension, the shape can be vary as much as it wants to. As long as it always meets that size.
Right.
So it
Wait.
controls the shape and that the shape can be anything.
Yeah,
you want
as long
it
as
to
the
be.
size is met.
Okay.
But you're turning me off on the diameter part. And I'm thinking diameter, I'm thinking circle.
Yeah.
So-
Diameter is just across the circle, right? When I
Diameter
measure straight through the middle,
I mean, there's a center
that's
point. at
that's
some
diameter,
point.
right?
I thought it was a circle.
But if you have a circle, you measure diameter straight through the middle, right? So this is supposed to be a circle, and I measure straight through center, and I get those. It's really exaggerated. But if I get those measurements, and no matter where I measure it, the measurement is between those two,
Still works.
then it's a good circle by rule number 1. Are those circles? Are those spheres? Are those perfectly round balls?
Nope,
Okay, let me just get back.
they're not perfectly round.
You've got a lot of other stuff in here. So, those are not balls, right? But look at this book when it rolls. Doesn't move up and down at all.
Nope.
So that means that those are the same measurement across it, no matter which angle it's pointing.
Do they qualify as a circle under those rules?
Under rule number 1, that is a perfect sphere. Because no matter which way you measure it, it is the same measurement exactly across the center.
Drilling a square hole.
What do you call, do those things have a name?
Yeah, things. I don't know what the name of it. They have a name. I don't know what it is. Same thing with the Pepto-Bismol bottle. If you go home and you have a Pepto-Bismol bottle, take it, measure it straight across, and turn it. It will be exactly the same measurement right across the middle, no matter which angle you
Rotate
turn it.
as a whole circle. I use that for a lever.
Always correct.
Hey, that's no problem. Something got stuck in it.
I don't have
I need to keep rotating.
a good end
Wow.
view.
So I have my- hold on to it, twist it.
Somebody loves pink.
That's the only thing that fit in that circle. That would give us some time.
You're looking for a picture of the thing?
Just put bottom of a Pepsi bottle.
There was one there.
It's like a bottom.
You know what it is though, right? It's kind of that same shape as those
Like a
things.
triangle,
Yeah.
but rounder.
And so, under rule number 1, that would count as a circle.
You could try.
So something kind of like that. Kind of like a triangle with the corners rounded off. It would count as a circle because no matter where you measure it, it's still the same thing. So that's why we do GD&T, because now this isn't really a good way. So if you wanted to be a perfect circle, what would you have to do?
Well, now you can't say.
Give it a
Let's say
radius?
without GD&T, if you just had regular tolerances and you wanted that to be a real close to a perfect circle, what would you have to do?
Radius?
Give us your comment.
Yeah, here would have to be,
Bro,
Real
you gotta
tight.
put the circular.
huh?
You gotta give it a circularity, right?
If we're doing it with just a regular tolerance, without GD&T, we'd have to make this real tight, right? Have to make that like to the 10,000th spot. So that way, it could still be an oval, but the oval would have to be a lot closer to the circle. But with GD&T, we could just tell it circularity within, so get rid of that.
Circularity.
So I could just come down and to a feature control frame and say circularity, then point 0.001. And so now the size has to be within the between that range. But anytime I measure the circle, its measurement would have to be within 1/1000ths. So going this way, if I measured that one 495, measured this way would have to be 496. If I measured this way as 505, then that would have to be 504.
Isn't
Nor
it
for
just
facts.
giving it extra work though?
No, it's making it less work.
How is that? I'm reading 3 different numbers just to get one simple shape when I can just get through all that and just get one
Because
simple measurement.
if you have to make this exactly perfect, and you have to make this one a real tight number, you're gonna make a lot of bad parts trying to make that one really good part. If you do this, now you have still a lot of size variation, but your circle, or the circularity of it, is a lot tighter control. So what would happen if you did it and you made it, and let's say, this measured that was 498 when you made it. Is that a good part or a bad part?
Bad part.
Bad part, right? Because these two numbers are more than 1/1000ths apart. So do I scrap this part?
Yeah.
I say yeah, no. I can fix it, right? How can I fix this part?
Make it smaller.
Shrinking
You
it?
can machine the outside down.
By shrinking it?
Well,
Just make it bigger, but.
yeah, make it bigger until those two meet. So if I had a little bit more control, maybe I go back in with a ream. I can ream it out, so maybe instead of being 495 on the bottom, I ream it out, so that's 497. So I ream it out another 2/1000ths. Now is that a good part?
Yeah.
Yeah.
Within that 1,000.
Or I could ream it out and made this one 50 and 499, right? So now I have a lot more control over turning that bad part into a good part.
Yeah, without scrapping.
Because I have that, but then I also have a lot of space here that I can make it bigger if I need to get that. Does that make sense now?
Mm-hmm.
How I can have a looser tolerance, but still have a lot more control and save me money.
By putting it.
So, little list of why GD&T is important. So, here we talked about the shape of the zone. So, we have round zones, more than just position. We'll talk about some more of those later. So 57% more tolerance zone. Oh, so 57.9, 60%. Also, the size of the zone can change with GD&T. We haven't talked about it yet, but by using condition modifiers, that size can change. Because if the hole is at its smallest size, the pin going in is going to have a real tight fit, right? And so it needs to be right in its tolerance zone. What happens if the hole gets bigger? Does it need to be lined up as exact anymore? No, it can move around a bit, right? So using regular tolerances, we don't get that. It has to be in the same spot no matter what size it is. GD&T lets us, if the hole gets bigger, we can move it around a little bit. So we can get more tolerance zone from it. And also, with GD&T, because of how we set the datums, and how we dimension and how we refer to datums in our GD&T, we're telling them exactly how to measure it. So that way, every part coming off is measured exactly the same way. So it's not being measured one way by one person, one way by another person, making the same part pass by one guy and fail by another guy. Now with GD&T, everything's measured the exact same way. So if they're made the same, two parts are going to pass, or that they're both going to fail. Okay? Questions? So the material conditions we have are MMC, which is maximum material condition, LMC, least material condition, and RFS. So what do you think maximum material condition is? So, what?
Smallest of the whole.
Yeah, the smallest that a hole could be. So we always we're talking tolerances, like last week, we always talk about holes and shafts. But it could be slots and things that go into slots. So a slot, so like that slot would be the same as a hole, right? This piece here would be the same as a shaft, right? Because this is going to go into something else. That'd be considered a shaft. That would be considered a hole.
Yeah.
So in that whole-
Or if I was, now this is the shaft hole, same thing as if it was round. The shape doesn't matter if it's male or female, basically. So, at max material condition, that's when we have a small hole or a big shaft. There's more material, the part weighs more, right? Maximum material. So if you can't figure out if it's maximum material, just is there more stuff in the part? That's maximum material condition. So what do you think the least material condition is?
When the part's hollow,
When the part weighs the least.
it's hollow.
So that means a big hole or a small shaft.
Oh,
Not hollow, because hollow is totally different. Because the hollow refers to more than just the feature we're talking about. What do you think RFS means?
Somewhere in the middle.
the reference part,
No.
radius,
What?
RFS.
Don't know.
I don't know what that.
Radio frequency system?
How does that have anything to do with
RFS?
tolerance?
I have no idea, dude.
Think in
RFS.
context.
Reference,
Talk
format,
Is it
script.
round something?
Okay, let's look at FS. What do you think FS stands for? What are we talking about?
We're talking about material.
We're talking about
condition.
features, so feature size would be a pretty good guess for FS, right?
Reference feature size.
So what do you think RFS means? If we have when the feature is the most mass, the feature has least mass.
Radius.
No.
Regardless,
Regardless.
regardless.
Why the hell would I think of regardless?
Regardless of feature size. So we have when the feature has the most mass, when it has the least mass, and when we don't care about how big it is. So RFS is kind of standard unless you specify. If you don't specify MMC or LMC, it's RFS. The symbols for them: maximum material, name of the circle around it, least material, the L, regardless, and R. So you usually won't see this. If you don't have one of these two, then it's regardless.
So you don't have to put it.
So
in, you should-
older drawings might have it. The newer ones usually don't have it on there. But it's still a term that you need to know.
Why-
So, what?
I would think legally you would want it there because somebody could always come back at you and say, wait a second.
No, because rule number 2 is RFS is always applied unless MMC or LMC is called out. So this is what takes care of that. This is why we don't show it, because unless you call it LMC or MMC, it's RFS. And some are always RFS. Like run out, total run out, concentric, and symmetric. Those are always RFS. Doesn't matter what size the feature is, they're always the same. So you cannot put LMC or MMC on any of these.
So circular, run out, butane.
Yeah, so on run out, total run out, concentric, and symmetric, doesn't matter how big it is, it's going to be the same. Right? Symmetric, we're talking about
The whole part.
how big, like the same from the center out. So it doesn't matter how big it is, it still has to be symmetric. Same thing with concentric. If you have 2 circles, the size of the circles doesn't matter. You still care about them lining up on the same center.
And the run out?
Same thing with run out. Run out is like circularity, but it's measured from the size of it. So next week we'll get in and actually go through a lot more detail of what the different ones are. So here are the GD&T symbols. So we have 5 basic categories. I don't know if that's where you're going,
Yeah.
but that's not 5 basic symbols, that's 5 categories. So we have the form, tolerances, so straight, flat, circularity or roundness, and cylindricity. And these ones we never use a datum with. These are always talking about the thing itself. So with flatness, we don't care about anything else. We care about that surface itself being flat. Straightness, we care about that piece of the surface being straight. And circularity, cylindricity, we care about that thing itself, unrelated to anything else.
So you use them in a feature frame without a datum.
Yep. So those would always be something like
The flatness plus
circularity.
yeah, diameter, whatever.
Something like that. You never have datum references at the end. Profile the line, profile the surface. We sometimes use datum reference with orientation and location. And right now we always have to have a datum reference. So we always have to, so if we're positioning something, we have to tell what we're positioning to. That's what the datum reference is. And if we're telling it needs to be concentric, it needs to be concentric with something else. Or it needs to be perpendicular to something else. So we always have to have another reference for that.
So I thought you said we don't use datums with the total runout.
No, we don't use modifier conditions with those. So this one we're talking about modifier conditions, LMC, MC, not datums. Here now we're saying which ones need datums, which ones don't. What do you notice about the form and the profile?
Basic,
What do you mean basic?
basic geometry.
No. What do you notice about these 6 symbols?
Basic line and circles.
Look at those. Do you see any patterns with those 6 things?
Lines and circles.
You know,
Keep going.
Conduit surfaces.
Keep going.
Which
If something similar, there's a pattern there. What's the pattern?
Are they all started from the lines, and they started cutting each other in half?
No?
Went from a square to a circle to a
No. There's a pattern.
They're all lines?
no.
There's, I mean, they're all lines. There's-
Oh, you could turn every single one of them.
No.
I have no idea.
We know.
What's the pattern?
What?
We don't know.
Did you guys
They all
look at
have a-
these? Like you're supposed to?
Yeah, I got one on paper.
What do you see about here? Let me do something. Now, do you see any patterns?
You said 6, no?
That's 6, right?
Yeah. Actually,
3 groups of 2. Now, do you see any patterns?
Yeah. Line, circle, arc. Or sort of, kind of.
Okay, there's another pattern.
Lines, circles, and combine.
They all have a base.
Look at these 2, then look at these 2, then look at these 2. Find the pattern.
Flat, round, flat.
One, the top
But
one.
they all use their top one in their second one?
Yeah. The top one is a basic thing, so straight and then flat, round, cylindricity. So the first one is kind of a 2D thing, right? Straight, we've got going along and then going up and down. Flat, we have X, Y, and Z. Circularity, we have in and out as it goes around the circle. Cylindricity, now we have a Z value for it also. So here, the first element is talking about an element of the surface. The second one is talking about the 3D shape of it. So, like, so if I was talking about this, I'd have straight, which would be if I measured straight across, and and straight across, and straight across, and straight across. That'd be straightness. And so the tolerance would only apply each time I went across. Each time I went across, it would apply individually. Flatness, I go across, and I take the highest overall and the lowest overall. Okay? So straight, the highest and lowest in one line. Flatness, do a bunch of lines, the highest and the lowest overall things. Same thing with cylindricity, or circularity around it. Circularity, I go around the circle, measure diameters, just the biggest and smallest diameter going around in one spot. Cylindricity, now I do that same thing up and down the cylinder and compare the highest overall to the lowest overall. And the same thing with profile of a line and profile of a surface. Okay? Does that make a little bit of sense?
Yeah.
So it's kind of a 2D and a 3D modifier.
Can you explain a little bit more on the profile of a line and profile of a surface?
I'll do that next week, or in 2 weeks. We'll get back to it.
Alright.
Today we want to get through the basics, and then we'll go in depth in some more of the symbols in 2 weeks. So the feature control frame, that we said already, it houses our symbols and our tolerances and our datum references. So you have it in here. First is our symbol, then is our tolerance, then is our datum references. So if we go to AutoCAD, where is the datum reference frame here? Or the feature control frame? Where is it?
Control frame, is
Annotate?
it down your
Yep.
lower left,
Nope.
or is it upper right?
Annotate. Then where? Yep, we go to the slide out for dimensions, and it's right there. It's also the shortcut, the alias TOL. So if I click on that, or if I just type TOL, it comes up. And it looks kind of similar, right? I click on the symbol, and I get to pick my symbol. So let's say I want position. Right here, I want to tell it I have a diameter symbol, so I want it to be a cylindrical tolerance zone. Tell it tolerance, so what do I want my tolerance to be?
0.002.
What's 0.002? What's that number? 2 thousandths. You're going to have to write out some numbers today.
Oh.
So that's 2 thousandths, because we're in the thousandths place,
Yeah.
and it's 2, right?
0.5.
This one after it, that's our modifier condition.
The L.
So do a maximum. Come over to datum 2. A, B,
C.
C. The box after that is if I want to add modifier condition to those. Say OK. Put it down. I click on it, grab any of the grips. All these grips act as move.
Why does it come in here?
So you can grab it from any corner
Oh.
so that you don't have to go to move and grab it. You can just grab the grip, grab it wherever you want, and drag it over. Because this is going to go onto so instead of having to go to move, I can just pick it, grip, bring it down. Okay. It's going to go something like that. That's the easiest way to add it in is just stick it onto a dimension.
I didn't know they had that.
What if we had a bunch of dimensions?
And then we'll get to
And
that.
just get a multi-liter and put it out there, or what?
We'll get to that. We'll get to where they go, and because where they go is important. So, questions on the feature control frame?
Sure.
So when our datums,
Flat.
we're putting here.
No.
So like this datum B, what we're doing is we're saying that our datum is actually a perfect surface lined up where that surface is. It's showing us the datum surface on the part, but the datum is an imaginary perfect plane at that location. Okay.
That way,
So these ways are all ways of defining the datum. So you can see it right on the surface. This little suction cup thingy, you have to draw.
that it comes out.
Yeah, that comes out on
Oh,
that.
that's a different program.
There.
Not in AutoCAD.
That's
Is
different
there an
program.
arrow for multi-leader that looks like that?
I don't know. I can look.
No, not a drawdown.
I don't use multileader that much, so I'll check. We can check. But in Inventor and SolidWorks it puts it on, but AutoCAD it doesn't. Let's do that right now.
The properties on that. Already scheduled.
Oh, datum triangle fill. Yeah, there we go. Content, frame text. Hey, what do you know?
Can't with it, huh?
Too bad it won't go straight down.
Put it from the.
That works.
Have you changed the landing distance?
Arrow head.
I don't know. You probably play with that to get it in a better spot. But that, good call. So you can use the multi-leader, and it'll make the sticker for you. What's my big problem with what I'm doing right now? Besides not having a thing that I'm dimensioning. What am I doing really wrong at this moment?
You're putting your dimensions in model space?
Yeah, I'm in pure model space, right? I don't want to be here. I want to be in my viewport in model space, right? I want to be in the model space viewport, not in pure model space.
Oh, you do your.
Because now it's remember when I put in that first one, it asked me
Gonna
what
be
annotation
scaled
scale I
differently?
wanted. So now these are the 1-to-1 annotation scale. So if I go to my template and I scale my part to a different one, then these are gone. I have to go back and add them in. So, good call, Darren. So, we can put these all here. And so, this one is defining this surface as a datum. So right here, that's B, that's the datum. A is defining the bottom. What's C defining as datum?
From that point to that point? The distance between those two?
No, C,
What else?
just that face. It's on the line, so we just bring it straight up.
Oh, okay.
You do it the.
What about this A down here? What's that?
The flatness of that piece?
Where's the datum for A?
On the bottom.
On the bottom of that.
Yeah, this
dimension.
bottom surface here. Where's the datum for B?
On that line.
That, on straight.
This line right here, right?
Yep.
So it's that surface, right? Not just the line, it's that surface. So is this datum B?
Wait, let me see if you.
This surface right here?
No.
No, because this surface is this, right?
Yeah.
So the datum B would be over here.
Yeah. So when you're doing the like on the one before, so when you're doing a part, and if you're doing that side view or whatever it is, you have to have the same datums on both sides, right? You have to continuously keep
No,
with them, or no?
no, this is just two different ways to do it. But I'm not gonna,
Oh,
I don't
okay.
repeat anything. I don't repeat A over here.
Oh, okay.
Because
So,
I can see that this bottom is the same as that one, right? So A is down here also.
so that's just two
B
different
is the
ones.
back side of that. C is the back side of this.
Yeah, I just saw two of the same things, that's all.
Well, that's just two different examples on how to do it.
Okay.
Usually this is what I prefer. Stick it on the extension lines, the dimension. If you don't have a dimension, stick it like that. I really don't like this one as much. And then we have this. So these are where we used to identify the center line or the center axis as the datum. So we can do that, that. We can also do that. So when we're in here, how can I edit that?
Right click,
I don't know what's right.
properties,
No,
override,
I got a lot of crap there.
so erase and override.
No. What's the better way to edit dimension text?
Delete and start over.
Nope.
No.
Double click.
Deleting isn't a good way to edit. Deleting gets rid of it.
Yeah, I just
Style
double click
it.
it.
Just double click in it.
No, double clicking didn't work.
Do what you were gonna add over there.
What, Kenny?
Edit.
Edit. What do I need to type?
ED.
ED, right? Edit text. I'm right back here. So then I datum identifier. I just put that A. Now I got it. So that's because this position is going for that hole anyways. So this is kind of what I would prefer here
Instead of putting the,
instead of
Yeah.
doing that's ugly.
that shouldn't be.
That's
right
kind of
anyway.
okay, or coming off of there.
Wouldn't that be wrong anyway, the first one, putting it on the top of the circle?
That's not wrong, but it's just not as preferred as
Yeah.
that or putting it like that, like that.
I like the third.
You know what those
What?
do look kind of somewhat clumsy.
But that first
Yeah.
one is.
I like that the way you want to do it over there in the box.
Yeah, it looks nice.
Making it part of the.
So then, where's datum A here?
Item A is
Where's datum A?
Straight down.
the line.
On that
the left
line.
Is it this line right here?
That surface right
Is it the surface right here?
Well,
there. Yes.
No,
Obviously,
Top,
no.
I think going this way.
no. How could it be the top? It's not
I
even
mean,
lined up at the top at all.
So what is it, sir?
But on the last drawing, you had it right there.
Yep.
Yeah.
On the last one,
B's right there.
it's right there.
So it's not the same.
This
Okay.
one, it's not.
The center plane.
What's
has-
different?
You look hell the same.
Center plane has datum.
Center line of the park,
Yep.
12 or 142.
So let's look at this one. And that one. So let's look at C and A. The C right here and that A right there. What's different about them?
Dimension.
That's just because
Just that center
that's-
mark is what's different?
Because this one, we already decided that this one is that surface.
Yeah.
Right.
And then this one is not that. What Darren said is it's the center of the part.
That's what it said. Center plane has-
What's different between that and that?
Well, it has a,
What?
Two sides.
two. No, that's just tolerance.
No,
This one has a tolerance too, it's just an entitled block.
Right.
It's lined up with the dimension?
It's lined up with the dimension. Being in line with the dimension means that you're talking about the center axis of that feature.
Wait a second. Oh, because
With
you're
the arrows
lined
in
up
line?
with the numbers.
Then you're talking about the center axis of that feature. If it's not in line, you're talking about that edge that you're on.
Right.
Big important thing. So where you put your dimension really matters. If you mean this, put it right in the middle. If you did it where you got your dimension there, and then you're going after your datum there, what's that mean?
Means sloppy.
Did you mean to line it up? Or do you mean not to line it up?
They're gonna call you back and ask you
They're
which
gonna
one do
call
you
you
mean?
and ask
Do you mean the
That-
surface
that's a
or do you
big
mean that
deal.
dimension?
Are they gonna
You need to either have it totally clear of it or lined up perfectly.
give you a box with your stuff?
Because what they would probably think is that you don't want it, that you mean this, you don't mean that center. But if you really meant the center, they're gonna say, oh, it's not lined up perfectly, even though they're touching it, it's not lined up. That's not what you meant. Goes to court, they're gonna look at the standard says line it up, it's not lined up, you lose your money. You pay for all those bad parts because you did that instead of lining it up. So, making sure where things are. Remember, what do I always say? It's the little things that matter, right?
Right.
Little things. Being off position just a little bit could cost $1,000 or millions, depending on how big of a project it is. So same thing here. Here they just took off the other arrow and put the sucker on. Okay? So make sure you know where you're lining that up. Questions? Let's go ahead and take a break. We've been at it for a while. We'll come back and we'll talk some more about datums,